subshells, where we have S, P, D, F as the subshells, and then within the subshells we have the orbits. Okay, we have the orbits. So this is the S orbit, this is the P orbit. Then we have what's the D, which we have 5. If this is 1, this is 2, this is 3, and we have the orbits. Okay, this is 5, this is 3, 1, 3, and 5. Because if we go, let's go get 7. Okay, right. So we look at the outer shell, which is the valence shell. Okay, the outer shell, outermost shell. Okay, now these ones here, the inner shell, they shield the outer shell from attraction. So when you have more inner shells, they will shield the outer one. That is why at the extreme end here, this becomes bigger than this, because of greater shielding. At the end, when it gets all the electrons up to 8, then it's like it's balancing out, and then it's bigger than the previous one, which should have been. As you go down, the charge density should be greater, so the size should be smaller. But at this point, you have 8 electrons, so you have the full configuration of the electron. So attraction is reduced by the core ones that you have. So this becomes slightly bigger than that. Alright, so this is in terms of simple shell number. Okay, and then as we go to this form the quantum numbers, as we go to the subshell, which was used based on the wave function by Schrodinger. Okay, so that goes, and then we have the filling system. The lowest is filled, then the second one you fill them single, and then double them. Okay, then the third one is exclusive principle. No electron can have the same quantum number. Any of the quantum numbers can have the same quantum numbers. No two electrons can have the same quantum specification or configuration. Right. So that is the Hubble principle. So that is the Pauline's exclusive principle. The Hubble principle is talking about the lowest energy. The Hans rule is talking about filling them singly before pairing them when you have the same energy level. Right. Now the next thing we're going to look at is hybridization. Now let's just first look at the configuration first. So how do we go about the configuration using the new method? Okay, so first, if you know the total number of electrons, let's say an atom has let's say 8 electrons. Okay, we can use the configuration. The first S, P, D, F. Okay, you usually have to fill the S first. So the S orbital. So this is the one S. Then we come to the next one, another S. Then you come to P. So this is the SP. Then you come to the next one. Okay. Then you come towards your D, which is 5. Okay. So it goes in that order. So when you are filling the electrons, so you see this is S, then you come to SP, the next is SP, SPD, the next is SPDF. Okay. So that's how it goes. Okay. So you have the 8 electrons, and then you have to ask to give the configuration, the electronic configuration. So 8. The first thing you do is you first have to start singing, fill the lowest single. But here we have only one of it. Okay. So the next thing is add the next one and turn the spin. So this is giving us what? 1s2. Okay. Now you come here. You come to the next one. You have how many left? You have filled 2, so you have 6 left. So 6, you go to the next energy level. This is 2. This is a 2. This is 1. This is the second energy level that we are going to. Okay. So we have filled the first. This is like the key. This is the second energy level that we are coming to. Okay. Right. So here we have 6 left. So you go 1. They are the same energy level. So go 1, 1. Sorry. You fill your 2 here. Okay, and then you come to the next one, the P. So this is the P, this is the S. Okay, by filling 2 here, how many we left? 4. So you have 1. You fill them here, you fill them singly first. Okay, then we left it 1 before you can add 1. So at the end you have 8. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be what 2s2, 2p4. Okay. So it means the configuration for 8 electrons will be what? 1s2, 2s2, 2p4. This will be the configuration. Okay. Right. So let's try another one. Let me clean that you can have a look at it. So the first shell has only S, the second shell has S, and then the P. The third shell have S, the P, then your D. So the fourth would have had what? In that order. So it's that it becomes, you repeat the top one, and this is going to go 7. Right, so here, let's say we are giving, now we are going to 12, let me go 10 electrons. Let's say we are told an atom has 10 electrons. We should show the electronic configuration. If we were using the old method, what we do is this is the nucleus, okay? The first one we take 2. The next one we take, when you take 2, we have 8 more. Next one we got 8. So this would have been what? 2, 8. This would be the old kind of representing electrons. So the first one, the first K is 2 electrons, can take maximum of 2, the next can take 8, so that's 8. Now if we are using the electronic configuration for this one, this is how it's going to go. The first one is taking 2, it will take 2 electrons, maximum 2. Then you come to the second energy level. This is S, this is S. So this 1S, this 2S, this 3S, this 4S, this 2P, this 3P, this 3D. And this is what? 4P, 4D, 4F. Okay? So we are filling for 10 electrons. So we must fill the lowest energy first. So the first energy, we fill 1, the next one, there's nothing there, so you have to fill the next one. You come to the second energy level. You finish first 1 before you go to the next one. So you fill 1, there's more electrons left, so you have to fill the next one. Always, you don't let them go the same direction. But then you come to, after filling 2, you have how many left? 6. So the first one, go 1, 1 first. Then how many be left? 3. So 3, okay. So when you are done, then the electronic configuration will be for these 2. Okay, and this is going to be 1s, 2 electrons, 2s, 2, and then what? 2p6. Okay, right. And you can tell which of them has 8 electrons. You know this 1, 8. This 1, 2, 3, 4, 5, 6, 7, 8. So that's where the oxygen has 8. That's 8. This is 10, right? 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So neon. This will be the structure for neon. Okay. So that is it. Neon has 10 electrons. If you represent it by this method, this is it. The KLM method, that is it. Electronic configuration, this is the answer. You can use this one too. Great. Okay. Now what happens is, I have to say this. When you are filling and you get between this one and this, anytime you are going to fill this one, come and fill 4S before filling 3D. Okay? It happens that this has a lower energy level than the 3D. So you have to come and fill it. So that is a point of note, something you should note, okay? Come and fill the 4S before filling 3D. Okay? That's something you should note. Right. And then the elements with electrons that alternate between these two. Because these two are very close, elements whose last electrons are within this electron, they can move from one another to the other. Okay, so they are the transition. That's why we call them the transition. They are the transition element or the transition metals. Okay, right. Now, having done that, let's look at something. Carbon. Let's see carbon. How many electrons we have? 1, 2, 3, 4, 5, 6. Carbon has 6. So So what will be the electronic configuration? So it will be 1s2. We have 6, so 1s2 we are taking 2. 2s2 we are taking 4. And 2p, what how many will have 2p? 2. Okay, so that is 6. Okay, 1, 2, 3, 4, 5, 6. So that is for carbon. Now let's see, we're going to use carbon to do some illustrations for bonding. When it comes to bonding, it is the outer shell which is used in bonding. The outer shell, okay? So this is the outer one. We have the piece, right? So that. Okay? So this is carbon. So what carbon will do is, before it can bond, it will undergo what we call hybridization. It will mix the orbitals. Okay, these are 2, this 2s, this 2p. They are the same energy. They have the same energy level. Okay, so they can be mixed. Okay, that is what we call hybridization. They can be, when they are mixed, they then attain the same energy level. Then they can use any of the orbits to bond. Okay, to form bond. So this is carbon. Okay, so what it will do is it will promote one of the electrons here to this one. Okay, so that we call it will be excited. So excitation will go on, and then we're going to have this. So we're now going to have that. So it is in its excited state. This is what it happens. Then it will mix this one. They all become hybridized. They will be mixed. Okay. To become they are mixed now, so they are kind of sp mixing. Okay, if it decides to mix just one s and one p, then it is sp. If it decides to mix one s and then maybe 2p, then it's sp2. It has to mix one s and the 3, then sp3. Okay, so this is sp hybridization, sp2 hybridization, sp3 hybridization. Okay, so if it is going to use just 2 bonds for bonding, it may just use the sp2 hybridization method. So just use sp to do the hybridization bonding. Okay, if it is going to use sp3, then to just use this one bonding. Now let's look at sp4. So it will use all the 4 for bonding. Okay, and that's typical of carbon. It may bond to hydrogen here, hydrogen there, hydrogen there, hydrogen there. Okay, so this one hydrogen will come and flow one hydrogen here, one hydrogen here, one hydrogen here, one hydrogen here to form the bonds. Okay, these are provided by, this is methane. Methane, it has 1 carbon. Okay, and it's used sp3. Now sp is a linear bond. Okay, so here we have mixed x and then the p bond. Okay, sp is a linear bond, so this is a linear kind of structure. sp2 is trigonal. So it means you have something trigonal. Okay, well let me put it this way. Okay, so that will be trigonal. Now sp3 will have 4 of that, 4 of the bonds. Okay, so it means like 4 of that. Okay, and that will be the kind of bond we call tetrahedral form. So this will be trigonal planar, this will be linear, and then this will be tetrahedral. Now let's look at something here, the angles. You see, so what will happen is, let me put it here. So our sp is like that. Okay, that is linear. This sp2 is like that. So this is 3, we have 3 bonds. So it's here. Okay, so you see that this one, the angle it's like three, it's planar, so this is trigonal, planar, it means it's plane, okay? And this angle, if you divide 360 into 3, that is about 120 degrees, okay? This one is straight line, so this is about 180 degrees, okay? And this is the trigonal. Now, tetrahedral is going to be something like that. It's going to have so this is the bonds and this one. Okay, this kind of thing. Okay. Right, so this is the tetrahedral shape. Okay, so this is 3-dimensional tetrahedral. Okay, right. Now, so we see that sometimes. So this is for carbon. Now let's see if it is not carbon and it's oxygen. Let's see what happens. If it's not carbon and it's oxygen. So carbon. This is carbon. The hybridization. Now, if it is, let's say if it's nitrogen comes before oxygen. So let's put nitrogen. If it's nitrogen we have many electrons. 1, 2, 3, 4, 5, 6, 7. So 7. That means 1, 2, 3, 4, 5, 6, 7. This is it. Okay. Now, if it is so, now how is it going to do the hybridization? Here it will be paired. So if it is now going to hybridize, here we can't excite it to move to another because they are all the same. So it will remain here, but the mixing will go on. So the mixing goes on straight away. So hybridization goes on. So this is going to mix. It can mix this and that. It can mix this and that. It can mix that. So let's say it is sp3. So it makes this one and all that. So you see that if it does so, it has only 3 spaces for bonding. Okay, this is where, so you have NH3 for instance. Hydrogen can come here, hydrogen can come here, hydrogen can come here. But this is part of the mix of it. It is the same level as this. So this can take part in a reaction. And that is what we call a lone pair, to have a lone pair here. So although this is sp3, instead of having one of the orbits will have 2. So let's say here has two electrons here. This is the lone pair. You can use it for bonding. Hydrogen atom can come on it to form hydrogen bonding. Okay. Now let's go if it is oxygen. Oxygen is what? Oxygen is 8. So we need to add this for 7. You need to add one more as 8. Okay. Then they will end up, there's no need to, you can't assign to any place. Okay. So they will mix or hybridize to form this. This is what you have. So how many spaces are left for bonding? Only 2. That's why oxygen will form 2 bonds, maybe with water. This is it. Okay. But this have undergone part of the hybridization. So they can also take part in reaction. So it will have what? 2 lone pairs, 1, 2. Maybe another one here. Okay, these 2 lone pairs can take part in hydrogen bonding. Like we said, hydrogen bonding is between lone pair and a polarized hydrogen. Okay, so these 2, so oxygen have 2 hydrogen bonds there, 2 lone pairs there. And then, so we can use this one to form a bond. Then this can use, let's say, here, the lone pairs here to form the bond. Okay, depending on wherever we put it. Okay, that is where they are. Now, but the point is, I should have talked about the angle. So you have 2 lone pairs. Okay, let's say the angle, not oxygen alone, I mean the sp3. What will be the bond? This one is 120. This we have 4. But the bond will come to like 104 degrees. The angle between each in 3-dimensional space. Okay, it's like 104. When it comes to some organic compounds, instead of having this bond, it may increase to maybe 110, especially in the ethers, because this one is a force, one force, this another force, this another force. The angle, let's say the angle at which the polar, the dipole moments do not cancel. Okay, right? And then the attached carbon atoms are so much that the repulsion that we were getting initially will be reduced. So it will open up a little, the angle will increase for ether and co. Right? So this is basically for hybridization that we've talked about. So we talk about hybridization for carbon, hybridization for nitrogen, and hybridization for oxygen. These are basic ones that you can use to that. We also talk about lone pairs that can be used in hydrogen bonding. Right. So this brings us to the end of this section.